Hello, welcome to numerical analysis class. This lecture is very useful for students in 200 level, particularly those that are doing FGS 261. Now, the question is, find the sum of the following appropriate numbers, each correct to the indicated significant digit. 136.436, 28.3, 321, 28.243, 17.482. Now, as we recall that in numerical analysis, particularly when we're working with computers, there are two basic errors that we may encounter. We have what we call round-off errors, and we equally have what we call the truncated error or chopping error. Now, in this question, we want to find the sum of these appropriate numbers. They have decimal places. Then we want to find the sum without using the calculator. And the sum we want to find is with respect to the errors that we are going to encounter. So in the course of this lecture, we will discuss, absolute error. We will discuss error due to round off and rounding off error. So at the end of the day, we find the value of the actual, data, the total data, the sum of the data. Then we now look for the errors as well. We add them together. But in this case, we are going to look for the range of errors because most times when we are given data in numerical analysis for us to analyze, there is the tendency that there will be error, either in approximation, truncation, or otherwise. So let's be patient enough to go through this process as we lead you into step-by-step teaching of how this can be done. Thank you. Now, want to find the sum of the following appropriate numbers, which are the significant digit given. Now, before we go, let's look at the first digit number. This number has how many decimal places? 1, 2, 3. This one has 3 decimal places. Okay. So the last digit is 6. All right. This one has how many decimal places? 1. Because the last digit is 3. This one doesn't have a decimal place. So the last digit is 1. This one has 3 decimal places. The last digit is 3. This one has 3 decimal places as well. The last digit is 2. So now let's clean this so that we're able to work here because the board is not big enough. Let's clean this. Okay. Let's clean this. Now, how do we start? Fine. The very first thing we are going to do is let's look at the direct sum first. The sum of the actual indicated numbers. What are the numbers again? Let's write them out. The actual sum would be equal to, we are adding everything together, 136.436 good plus 28.3 plus 321 plus 28.243. Okay. Hope that's okay. That's not clear. It's not clear enough. It's not clear enough. Let's rewrite it. Sorry about that. 136.436 good plus 28.3, yes, plus 321. Let's add the other one there. Plus 28.243, then plus 17.482. So if we add everything together, we're going to have what? 531.461. So that is the actual sum of the numbers. Good. Now, from all these numbers, before we can find, we actually need to find the error of each number there. You need to find the error of each number, and to calculate the sum of errors of the original data, the very first thing we are going to do is this, to calculate the errors of the original data. Now, let's look at which of this data, or like we have said before, we said this one has 3 decimal places, this one has 1, this one has no. Now, the number we are going to deal with here, before we can get the error of actual data, is let's look at the number that has the least decimal place. Now, the number with the least decimal place here is 321. It has no decimal. Fine. 321 has no decimal. Very good. So since 321 has no decimal, we pick it up as a case study. It gives us as a reference data. The others have more than, like this one has one piece of decimal, 3, 3, and 3, and so. Okay. Now, so 321 is going to be our what? Focus. It's going to be our reference data now, the one we're going to use. Now, this 321 has 1 as a digit, as the last digit rather. So now, if you want to look at how to find the errors of others, how to round off or how to round the other values off, we're going to write round other value off using the values of the units we have here. How? What do I mean? Fine. Since we are picking since what a fork. Since we choose 321 as choose 321 as what? As the number or the digit number with the least what? The least decimal. Then we round up others. We round up other numbers to 0.1. Let's round up other numbers to 0.1. How? What do I mean by rounding up? Very good. Good. Since it doesn't have a decimal number, so other numbers will be rounded up to the least. Since the decimal number here is 0, so rounding off other numbers, the actual numbers rounded up will be to just one decimal place. That's what I'm saying. It's at 0.1. How? Fine. Let's say that let's use the first error. Let's call it E1. Okay, let's call the first error E1, which is sum of the error of the sum of the actual data. Errors of the sum of actual data. Sum of actual. So the actual sum data or value, or we can say digits. Okay. Now, good. Now here, let's pick the first one. The first one here is 136.436. So the decimal unit here is 3. So we're going to have what? 0 points. You have 0 here, 0, yes, replacing this 0 here, 1. The last one before 1. Where do I see 1? Fine. This is in thousands, because we have 3 decimal places here. And 1,000 has 3 zeros. So this is like 1 over 1,000. This thing is like 136 all over what? 136,436. So because we have 3 digits number here as decimal places, then it's going to be 1. Our value will be what? Now I'll say that this place is 1, 2, 3. This 3 now replaces this. Now the other one, the next one here, plus. How many digits does this have? It has only 1 digit. So that would be what? 0.1. Yes. 0.1. So 0.1 has only 1 decimal digit. Then plus 321 is 0 because it doesn't have the decimal number. Then plus this one has how many decimal number? So it will have what? 0.001. Just 1, 2, 3. This 1, 2, 3. That will replace that. Then the next one is what? 1, 2, 3. 0.001. So by the time we sum this up, it will give us what? 1.103. So that's the what? The errors from the actual digit. That's the error from the what? To calculate the sum of the original errors from the actual digit. Now, let's look at the second error. Look at the second error. Want to look at the second error. You can take note of this. And how do we look at the second error? Fine. That is not difficult at all. Now, in the second error now, we have to take cognizance of, we call it the second error now will be absolute of the round-off error or rounding error. Absolute of it. We want to take this, so the absolute, the sum of the absolute value of sum of rounding off error. Now, how do we go about this? Let's write the numbers out again. Let's write the number out again so that it will be easy for us to look at. 136.436, good. 28.3, 321, 28.243. Yes. I will rewrite it. Don't worry. I think those are these the numbers? So the absolute value of some of the rounding errors. That's what we want to find now. Good. Now, don't worry, I will rewrite it. You will see it clearly. Okay? Don't worry, I will write it. I will take it one by one now. Now, we want to find the what? Absolute value of some of the rounding errors. Absolute value of some of the rounding errors. Call that one error 2. Absolute value of some of the rounding errors. So that's what we want to find. Now, let's pick the first number. You know, the first number is 136.436. Good. If we round it, we round this number, we round it off. So let's say we approximate it. Don't forget, we are approximating to 0.1, which we obtained from 321. This 321. So when we approximate, we have what? 136. When you approximate to 0.1, it means you want to approximate to one decimal place. That's 0.1. If it was 0.01, it will be that's two decimal places. Okay, fine. Now, when we approximate this one, as one decimal place means you count only one number after decimal. Are we following? Good. Now, only after decimal here, the only number we have here is 4. Now, go to the next number. Is it up to 5? No, it's 3. So you chop off others. So you chop it over. So that 136.4. So the remaining numbers there will be 0. You can write 0, 0 if you like to replace them. Because after the first count, a number after decimal, the next is not up to 5. You can only approximate a number that is, 5 upwards. Okay. Now, what is the error here now as a result of this approximation? There's an error because we have truncated 436. So the error will now be, this one implies you subtract 436, so you see minus 136.400. So you write that. So what is the value you're going to get there? You're going to get what? 0.036. I think. Yes, 0.036. That is the error for that one. The next one, 28.3. Let's approximate it to one decimal place. 1. After decimal, you count 1. It doesn't have any value thereafter. So we have 28.3 as well. So that means you subtract this from this as well. 28.3 minus 28.3. That gives 0. Fine. The next one, 321. If you approximate it to, originally it doesn't have a decimal value. Okay? So it's still going what? 321. So you subtract 321 from 321. 321 minus 321. That gives you what? 0. Beautiful. Let me clean this. Let me clean this. Let me clean this. Okay. Now the next is 28.243. Approximate it to one decimal place. You count one number after decimal. So the next is not up to what? It's not up to 5. So just remember that 28.200. Okay. Now that means the original number, the actual, will be what? 28.243 minus 28.200. And that will give us what? 0.0. That will give us 0.043. Okay? Yes, 0.043. I hope that is taken. Beautiful. Now, the last one, 17.482. Oh yeah, approximate it to one decimal number, 1. The next number is up to 5, even more than. So it becomes 1. 1 plus this 4. So that's 17.500. So in this case now, what is the difference? That will be what? 17.482 minus 17.500. That was 0 minus 0.018. Good. That's minus 0.018. Now, for us to find the error 2, for us to find the absolute value of sum of the random errors. I want to find the absolute value of sum of the random errors. Let's first of all add them together to find the absolute value of sum of the random errors. Let's add them together. Oh yeah. So let's say E2, error 2 is absolute value of sum of the random error. Sum of the random errors. Before we can get that, we have to what? We have to first of all add them. Okay, let's add them. Now we have 0.036, yes, plus 0 plus 0 plus 0.043, good, then minus 0.018. Yes, let's add that. If we add that, what are we going to get? Adding that together, we should be able to have what? 0.061. So check 0.061. So we had everything together. So you can clean that. Let's clean this. We are done with this. 0.061. That is the result we are going to get. So that is for error 2, which is absolute value. Now, what is the absolute value of this now? So error 2 will now be absolute value of what we have there. 0.061. It's still what? 0.061. Beautiful. Okay, you have to first of all add them together before you now find the absolute value. That is it. Okay, now the third one is the round off error. Call it round off error. It's different of round off error. Round off error. The sum of, let's say, sum of round off error. Okay, sum of round off error. And how do we round off? Yes, error. How do we get that? Fine. You know, we use 3, 2, 1 as our case study, as our base for the determination of the errors of individual appropriate number. Now, and if 321 has we approximate other ones to 0.5. Okay. Now, the absolute value error, actually here, would be what, when multiplied by 2, which would be what? 0.05. But because the last digit here is 1, yes, because it doesn't have a decimal place, it doesn't have a decimal number, and the last digit is 1. So you divide that 1 by 2. Okay, so that was 0.5. So the sum of round off error is 0.5. Yes, that's the base there. Because what we are saying is that the round off error now we are expected to have should be 0.5. If it has the number that has one decimal place, the round off error will have been 0.05. Okay, so but since it doesn't have, so it doesn't have what? It doesn't have a decimal at all. So the round off error should be what? Approximately 0.5. Okay. Now, how do we now get our error? So error E will be error 1 plus error 2 plus error 3, which is, what is the first error? What did you get for the first error? Do you remember what we get? I think it's and what is the first error? What did you get for the first error? Fine. The first error, I think, is to calculate some of the errors of the original data. That is what? Fine. 1.103. That's the errors of the original data. The sum of the errors of the original data is E1, and the other one is E2 is what? Absolute value of sum of the round off error. Absolute value of sum of the rounding errors is different from round off error. Don't get it wrong. Absolute value of sum of the rounding errors, E2, we got it to what? 0.061. Then plus the round off error, 0.1. So let's add them together. Let's add that together and check what we're going to have. Okay. 0.061 and 0.50046661. So we're going to have what? 1.664. So we are going to get what? 1.664. Now, the sum required, therefore the sum required will now be equal to the actual sum 531. But don't, this time around, we are going to approximate the actual sum. The actual sum was 531.461. So you approximate the actual sum. The approximated value, let me write it like this. The approximated is equal to the approximated value of the actual sum plus the errors, plus error E, or let's say sum of the errors. Okay, the approximated value of the actual sum plus sum of the errors. But yeah, let's go about that. Now, when we the approximate value of actual sum, we got what? That was what? 531.461. So it is approximated to what? Let's write it there. 531.461. Approximated to what? 531. That is the approximated value of the actual sum when we had it together actually. Good. So we approximate it. Now don't forget we are actually looking for errors. Good. So now that will now be what? That now implies 531 plus what is the sum of the errors you have gotten? 1.664. And don't forget, in the actual sense, we have to make provision for either the error is decreased, or the value rather is decreased or is increased. Okay, so in that case now, we also approximate this. We are going to approximate 1.664. So that would what? 531 plus or minus. If you approximate 1.664 to a digit now, to a digit or to one digit or to one significant figure. Okay, we need significant this time around. So, after the count of 1, the next number is 5. So 5 is rounded off to 1. So 1 plus 1 is 2. So the answer will not be what? 531 plus or minus 2. So the required sum, or the sum required from this problem, is 531 plus or minus 2. So with this, we have come to the end of this problem in numerical analysis. Don't forget, this is an example of sum or addition of appropriate values of numbers, which records to the sum of errors, and we are making a provision for either addition or subtraction of the actual value of the digit number given to us. So if you are joining this channel for the first time, don't hesitate to subscribe, click the notification bell so that each time I upload a video, you're immediately notified. And if you actually enjoy this video, click like, share, and comment. God bless you. Bye.